The morning context of this analysis begins with a simple observational prompt, a sunrise jog followed by a sketch meant to capture the physical intuition behind a faint, fuzzy glow seen in a Hubble Space Telescope image taken on July 21, 2025. That glow surrounds the newly identified interstellar object 3I/Atlas, and while it may appear visually subtle, it encodes a remarkably rich set of physical processes involving dust ejection, interaction with the interplanetary environment, and momentum balance on scales far larger than the object itself. At its core, the phenomenon is an extended dust outflow illuminated by scattered sunlight, forming a roughly symmetric halo that stretches thousands of kilometers into space. Understanding why this halo has the size it does, and what it reveals about the physical nature of 3I/Atlas, requires tracing the journey of dust particles from their origin on the surface of the object to the point where their outward motion is halted by the surrounding medium. One of the most striking coincidences in the case of 3I/Atlas is the near-perfect alignment of its trajectory with the ecliptic plane, the same plane in which the planets orbit the Sun and in which the interplanetary zodiacal dust is concentrated. This is not merely a geometric curiosity. It has direct physical consequences for the evolution of the dust outflow. The zodiacal dust cloud is a diffuse but pervasive component of the inner solar system, composed of microscopic grains shed by comets and asteroids over billions of years. Although tenuous, this medium becomes dynamically important when a fast-moving object like 3I/Atlas plows through it at tens of kilometers per second. In the reference frame of the object, the zodiacal medium appears as a headwind, exerting a ram pressure that can oppose and eventually stop the outward flow of material ejected from the surface. The Hubble image reveals that the scattered sunlight extends to a characteristic distance of about 3,000 kilometers in all directions from the object. This scale is not arbitrary. It reflects the balance between the outward momentum flux of the dust outflow and the inward ram pressure exerted by the ambient zodiacal medium. Near the surface of 3I/Atlas, dust particles are launched with some characteristic ejection speed and mass density. As they stream outward, the flow expands roughly spherically, and its mass density decreases as the inverse square of the distance from a nucleus. This dilution is a geometric consequence of mass conservation in an expanding flow. The same amount of material must pass through ever larger spherical shells as the distance increases. By the time the outflow reaches a radius of 3,000 kilometers, its density has dropped dramatically. If the nucleus of 3I/Atlas has a radius of about 10 kilometers, as inferred from its brightness assuming a low albedo of roughly 5%, then the ratio of the stopping distance to the nucleus radius is about 300. Squaring this ratio gives a dilution factor of about 90,000, meaning that the mass density of the outflow at 3,000 kilometers is nearly 5 orders of magnitude lower than it is near the surface. Despite this extreme rarefaction, the outflow remains detectable because even a small number of dust grains can scatter sunlight efficiently when illuminated by the sun. The ejection speed of the dust is a critical parameter in this picture. A strict lower limit on that speed is set by the rotation of the object itself. With a reported rotation period of about 16 hours, the equatorial surface speed of a 10-kilometer radius body is only about 1 meter per second. If dust were merely lofted by centrifugal effects, one would expect velocities of this order. However, the morphology and extent of the observed halo suggest that the dust is moving significantly faster. Detailed analysis of the Hubble image indicates an ejection speed of roughly 20 meters per second for dust particles with characteristic sizes of about 1 micrometer. Such speeds are consistent with weak gas drag from sublimating volatiles or other surface processes that can accelerate small grains beyond the rotational velocity of the nucleus. Once ejected, the dust carries momentum into the surrounding space. The relevant quantity for determining how far the dust can travel is the ram pressure of the outflow, defined as the product of its mass density and the square of its velocity. This ram pressure represents the momentum flux of the outflowing material. As the dust expands outward and its density decreases with the inverse square of distance, the ram pressure declines in the same way, assuming the ejection velocity remains roughly constant over the scales of interest. Eventually, this declining ram pressure becomes equal to the opposing ram pressure of the ambient zodiacal medium, at which point the outward motion of the dust is effectively halted. In the rest frame of 3I/Atlas, the zodiacal medium flows past the object at a speed equal to the object's velocity relative to the Sun, which is about 60 kilometers per second. Even though the density of the zodiacal medium is extremely low, of order 1 proton mass per cubic centimeter, the high relative speed makes its ram pressure non-negligible. Ram pressure scales with the square of velocity, so a speed of 60 kilometers per second amplifies the effect of even a very tenuous medium. By equating the ram pressure of the outflow at the stopping distance to the ram pressure of the zodiacal medium, one can infer the mass density of the outflow at that distance. From this calibration point at 3,000 kilometers, the inverse square scaling of density allows the mass density of the outflow near the surface of the nucleus to be extrapolated. Once that surface density is known, estimating the total mass loss rate becomes straightforward. The mass loss rate is simply the product of the mass density at the surface, the ejection speed, and the effective area over which the material is being emitted. For a sunlit object like 3I/Atlas, it is reasonable to assume that most of the activity is concentrated on the sun-facing hemisphere, so the relevant area is roughly half the surface area of a sphere with the inferred radius. Carrying out this calculation yields a mass loss rate of about 10 kilograms per second. Remarkably, this value agrees closely with independent estimates derived from more detailed modeling of the Hubble image, lending confidence to the underlying physical picture. The agreement suggests that the observed halo size, the inferred dust velocities, and the assumed properties of the zodiacal medium are all broadly consistent with one another. It also implies that even a modest level of activity on a small interstellar object can produce a detectable and dynamically significant dust environment when the object passes through the dense regions of the inner solar system. An especially elegant aspect of this result is that the inferred mass loss rate does not depend on the assumed radius of the nucleus. This may seem counterintuitive at first, since the surface area clearly depends on radius. However, the key lies in how the surface density of the outflow is inferred. Because the density at the stopping distance is fixed by the balance with the zodiacal medium, and because that density scales inversely with the square of the distance from the nucleus, the inferred surface density scales inversely with the square of the nucleus radius. When this surface density is multiplied by the surface area, which scales as the square of the radius dependence cancels out exactly. The resulting mass loss rate is therefore robust against uncertainties in the size of the nucleus, at least within the assumptions of the model. Beyond the purely mechanical considerations, there are additional layers of complexity that may play a role in shaping the observed dust halo. Dust particles in space often acquire electric charge through interactions with solar ultraviolet radiation and the ambient plasma. Charged dust grains can interact electromagnetically, potentially leading to collective effects such as filamentation or deviations from purely ballistic motion. While such effects are difficult to quantify without detailed plasma modeling, they could influence the fine structure of the outflow and contribute to subtle features in the observed brightness distribution. In the broader context of interstellar objects, 3I/Atlas offers a unique laboratory for studying how material formed around another star behaves when exposed to the environment of our own